Today's lesson is going to be about equilibrium expressions and calculations. So the relationship between the concentration of products and reactants at equilibrium can be expressed by what's called the equilibrium constant, which we call KEQ. We can also call it KC. It can also just be regular old K. All of those would mean the same thing. As we learned in our last unit with acids and bases, these square brackets tell us that we're talking about molar concentrations, right, which is referring to molarity. Okay. So when we write the equilibrium expressions, the reactants or products that are pure solids or pure liquids do not appear in the expression because it does not matter how much of those that you have. Okay. It is considered to be pure, and so pure before the reaction and pure after the reaction, then the concentration does not change. Okay, so the only things we're going to be really concerned about with equilibrium expressions are those things which are aqueous or those things which are gaseous. Okay, so aqueous and gas. Okay, so if we look at this example here, the generic expression for the reaction, little a, little b, the lowercase letters are referring to the coefficients. The uppercase letters are the substances. Okay, and so here we would have the products over the reactants. So our product D, which is aqueous, raised to the D power, right, is coefficient. Now we leave out C because C is a solid. Okay, and then we have A raised to the little a power, again its coefficient on the bottom, and B raised to its coefficient as well. And those two things are multiplied together. Okay, so again, only those things which are aqueous and gas are included in the equilibrium expression. No liquids and no solids. Okay, and again, that's why we did not include C. All right, so let's talk about the constant KEQ. If KEQ is greater than 1, that means that our top portion is larger than our bottom, right? So we have more products. So you have more products at equilibrium, okay, than reactants. If KEQ is, well, that should be less than 1. We'll have to change that to less than 1. Right? Then you would have your denominator is larger, right? So you would have more reactants at equilibrium. Okay, so let's write some equilibrium expressions. So the first one we're going to write over here in the box for A. So K will be equal to, again, our products. Okay, so we need to make sure this is balanced first. So we have 3 and 4 oxygens, and 2 and 2 make 4, and 1 and, okay, so we're good. So our products are O2, and its coefficient is a 1, times NO2, and its coefficient is a 1, right, divided by the concentration of O3, and its coefficient is a 1, times NO, and its coefficient is also a 1. So the equilibrium expression would look like this. So letter B, again our K would be equal to concentration of CO2, which is our product. Now this time it has a coefficient of 2, so it's going to be raised to the second power, divided by our reactants, CO, which is raised to the second power, again because it has a 2 coefficient, times O2 to the first power because this coefficient is a 1. Okay, so pause and you do C and D, and then come back and we'll check. Okay, so for letter C, remember we cannot include our liquids or our solids, Okay, so we do not include those in our equilibrium expression. So our equilibrium expression would just be that K is equal to the concentration of N2O. Right? And then for D, all of these are gaseous products and reactants. And so we have our hydrogen raised to the second power, because its coefficient is a 2, times the oxygen raised to the first power, divided by H2O to the second power. Okay? Alright. So let's look at some calculations. Alright, so the calculations of the gases involved in the reversible reaction at equilibrium are known as equilibrium concentrations. Okay, since equilibrium represents the system, since the KEQ represents the system at equilibrium, only these concentrations can be used in the equilibrium expression, not the initial concentrations. Later we'll talk about how we solve problems with initial concentrations when we do the ice charts in a couple of videos. Alright, so the first thing we want to do is to set up our equilibrium expression. So our K is equal to the concentration of our products raised to their coefficients. These are all a coefficient of 1. Okay. Now, it says, what is the equilibrium constant? So that's K. If the equilibrium concentrations are, so PCl5, right, has concentration of 0.0096 moles per liter, right? And then on top we'll have our PCl3, which is 0.0247 moles per liter, times 0.0247 moles per liter, right? And so when we multiply and divide, then we'll get our value for K. We should come out with 0.064. So let's make sure we can get that in our calculators. Alright, and we get 0.064, and that is the correct number of significant figures because we started off with just the 2 over here, and these each had 3, so we can only keep 2. Now K does not have any units. Okay, it is unitless. Right, K is unitless. Right, no units. Alright, so you try the next one. Pause, and you can come back and I'll go through it with you. Alright, welcome back. We're going to write our equilibrium expression first. So we have NH3 squared over N2 times H2 to the third power. Alright, so this time we have a 1 liter container, and the equilibrium mixture contains 0.102 moles of ammonia, 1.03 moles of nitrogen, and 1.62 moles of hydrogen. Okay, again, these are moles and we have to have molarity. But this time, luckily, we have 1 liter, and so the molarity for each would be the for the ammonia would be 0.102 moles divided by 1 liter would still be 0.102 moles per liter. Okay, so we can then plug that in for ammonia. So K would be equal to 0.102 moles per liter, or molarity, squared. And the same will be true for the others, right? So this is the ammonia. And then the nitrogen, its molarity would be 1.03 moles per 1 liter. And again, we get 1.03 moles per liter, molarity. So we plug that in. And that's to the first power. And then the same for our hydrogen. Its molarity would be its moles divided by 1 liter. And again, it would be 1.62 moles per liter. But this one's going to be raised to the third power. Now this is where your calculators might be a little tricky for you. So you want to make sure that you use parentheses correctly, or that you simplify first. Okay? So if you just want to use your parentheses, you can just do 0.102 and then square. Then you would have to hit divide, and then you would need parentheses. Then you would do 1.03 and then times 1.62, and then caret 3 to raise it to the third power, then close your parentheses. And you would get, for K, 0.00238. And we have 3 significant figures, so we keep 3 significant figures, so 0.00238 is our equilibrium constant. Alright, and this concludes today's video.